Hi, everybody. Happy Friday. So today is Friday, January 27th. You have session 7.3 and apps? Good. Okay, so today we'll start at 7.3. And then your homework is due next Wednesday. Remember, you submit your first attempt by the Wednesday midnight. And then after the deadline, you can still continue to do your homework until you get perfect scores. And your homework has a solution, and also some of the questions has videos, right? If you have questions, also feel free to ask me. Okay, so let's start 7.3, the definite integral. So in section 7.1 and 7.2, we talk about the antiderivatives, and we also compute the indefinite integral. Indefinite integral is we have the integral sign, but there's no bounds for it. Okay? So indefinite integral, you get a family of antiderivatives. That's why you have the plus c. Okay. And this class, let's talk about the definite integral. So our goal is to find the area under the function. Okay, we know derivative is the slope of the tangent line, right? And integral is actually the area under a function. So how do we find the area? Let's start with finding the area of some basic geometry figures. So this is a rectangle. The area is length times width. Yeah? And we have the triangles. So how do we get the area of the triangle formula? Well, you start with a parallelogram. Oh, okay. Let me get this smaller. Okay. So you start with a parallelogram. Let's say this is B and this is H. And what do? Is you cut this piece and put it here. Do you see you get a rectangle? Uh-huh. So therefore the length is exactly the same as the B and the width is the height. Therefore for a parallelogram is base times height. And then triangle. You see? You get another copy of the triangle and you flip it upside down and paste it. You get a parallelogram. So a triangle is half of a parallelogram. That is 1/2 base times height. And polygon. Once you know how to calculate the area of a triangle, for polygon, you just cut it into a lot of different triangles. You compute the area of each, and then you add them up. So this is how we find the area of geometry figures. And how about circle? Do you remember the area of a circle? Pi r square. Yes, the circumference is 2 pi r. Yes, the area is pi r squared. Good. Okay, but however, it isn't easy to find the area of a region with curved sides. See, this is curved. How can we find the area? Okay, the method is to evaluate the area of the region. We first approximate it by the rectangles, and then we take the limits of the area of the rectangles as we increase the number of rectangles. So the idea is we cut a lot of rectangles and we compute the area of each rectangle. And if you let the number of the rectangles go to infinity, then the area of the rectangles will converge to the actual area of the rectangle. Okay. So let's see. Example. This is a forward example. We want to use 4 rectangles with the right endpoint to compute the area of the rectangle. B, use the left endpoint. Or C, use the midpoint to estimate the area under the parabola. By the way, parabola looks like this, right? And +1 means you shift up 1 unit. So therefore, the y-intercept is 1, and then the parabola opens up. Okay? When you plug in x is 0, you get y equals 0 plus 1 is 1, right? And when you plug in x is 1, what is 1 squared? 1. 1 plus 1 is 2. Do you see here at the point 1, our y value is 2. How about when you plug in 2? 2 squared plus 1 is 5. See? So 2 here. Oh, I get my y is 5. So you can put the points and then you can draw the function. And this example tells us we want to use the left endpoint. Sorry, part A, right endpoint. Okay, so we cut it into 4 rectangles. So we cut this into, let me get my orange color. So this one, this one, this one, and this one. So we want to cut it into 4 rectangles. But look at the first rectangle. Which point do you want to choose to be its height? Part A, it tells us that please choose the right endpoint. Do you see the right endpoint is the 0.5? Mm-hmm. So we use right endpoint and we draw the first triangle. Not triangle, rectangle. Yes. And the second rectangle, we also choose the right endpoint and draw it. This is what we get. And the third rectangle, choose the right endpoint and draw it. We use here. And then the last one, choose the right endpoint and we get this. Okay, so we have 4 rectangles. And we want to compute the area. The area is the length times width, right? And you can see the width, they're all the same, which is, what's the difference here? 0.5. Yes. So our width is 0.5. And our height. Look at the first rectangle. The height is f of 0.5, right? So that's why we have 1/2 is 0.5 times f of 0.5. The second rectangle, 1/2 times f of 1. Next rectangle, 0.5 times f of 1.5, which is 3/2. And then the last one is 1/2 0.5 times f of 2. Okay? And then we plug in 0.5 into the parabola and plug in 1, plug in 1.5, and plug in 2. And we add them up, we get 5.75. Is that okay, everybody? Mm-hmm. So we compute the area using the right endpoints. That's why you see R, stands for right endpoint sum, with number 4 rectangles. Okay, that's the notation. Okay, part B. How about we use the left endpoint? So the first rectangle, use the left endpoint, and this is what we can draw. Right? The second rectangle, use the left endpoint. So we get this. And then the next rectangle, use the left endpoint. That's why we get this. And then the next one, use the left endpoint. That's why we get this. And now, again, width times height. So width is always 0.5, right? We have the same width. But here, the height is f of 0. Attendance. Okay, so here we have f of 0, right? So 0.5 times f of 0. The second rectangle, 0.5 times f of 0.5, right? And the next one, 0.5 times f of 1. Next one, 0.5 times f of 1.5. That's why our answer is 3.75. Do you realize this number is bigger than that? Makes sense, because here you have more area than this one, right? And our actual number should be between those two numbers, okay? Yeah. This one overestimates, this underestimates. Our true value should be in between them. Okay, so part C. Use the midpoint, the middle point to estimate. Do you see the first rectangle? The width is always 0.5, but you use the midpoint. What's the midpoint? 0.25. Yeah, so this is f of 0.25, and this is 0.75, right? So f of 0.75 here, 1.25, right? So the height is f of 1.25. Here, 1.75. So f of 1.75. So now we compute the area. We get 4.625. I would say the actual area will be closest to the 4.625. Okay, everybody? Yes. All right. So that is this example. Now is our turn to work on example. Now, example 1. Use the right endpoint Riemann sum. Okay, actually they're called the Riemann sum. Riemann is this idea using the sum of rectangles to approximate the area. Okay, so let's see. We draw the picture. Help us understand. And this is the x. That's the y. And the function e to the 3x minus 1. And we want to compute from 1 to 4. If we plug in 1, what happens? E to the 3 times 1 is 3. 3. Oh, sure. Yeah, 3 minus 1 is 3 minus 1, 2. Yes. So we have 0.
Sounds like you're charging a computer better for class.
Yeah, I should do that.
You can plug it in when you get in.
Yeah. I need to build this habit.
It's got to prepare for class. It's got to put your phone, you got to plug it in.
Okay. So 1, 2, 3, 4. Sorry, forgive me getting old. You know, when you get okay, who am I? What am I going to? Yeah. Okay. So yes, 1. We plug in 1. We get what here? Like e squared, right? 1. And let's plug in 4. If we plug in 4, what happens? E to the. If we plug in 4, yeah, e to the 11. Ooh, it's such a big number, right? So we get this. So we know our picture looks like that. Okay, so we want to cut 6 subintervals. So we have 6 rectangles. How many are there? 1, 2, 3. 3 subintervals. We need 6. So each of them we just divide by 2. Okay, so we have this one, and this one. So this is 1.5, 2.5, and 3.5. Draw the picture. Right, everybody? Okay. So now we see. Okay, use the what? Right endpoint Riemann sum. So the first picture, use the right endpoint. Yeah. So we use this one. And second picture, right endpoint. right hand point, right hand point, right hand point, and right hand point. And this is the rectangle. Is that okay, everybody? What is the width? Yes, so 0.5 is the width. So we get our integral. So this is a definite integral from 1 to 4. And this function is e to the 3x minus 1. So this is definite integral. It represents the area under the curve from 1 to 4. And now we want to use the right Riemann sum with n equals 6 to approximate it. Okay, let's add the area of those 6 rectangles. Okay, the first rectangle, what's the width? 0.5. Yes. The height is f of which point? Height is f of 1.5. Yes, so we got, let me put here, 0.5 times f of 1.5. That's the first rectangle. How about the second rectangle? What's the width? Yeah, 0.5, and the height is f of 2. Yes. So 0.5 times f of 2. Next one, 0.5 times f of 2.5. Can everybody see it? Mm-hmm. And then 0.5 times what? Next rectangle. F of 3. Next rectangle. Yes. And the last one. Yes, very good. Right? Do you see all of them have the common factor 0.5? Let's factor out the 0.5 because I don't want to type the 0.5 in my calculator 6 times. Do you want to type it 6 times? No. So now we have f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5 plus f of 4. Okay. Now, we need to look at our function f. Our function f, this is the f of 1.5. F of 1.5 is, what is 3 times 1.5? 4.5 minus 1. 3.5, yes. So e to the 3.5. Keep going. F of 2 is, what's 3 times 2? 6. 6 minus 1. 6 minus 1 is 5. Yeah, everybody? Okay, continue. 2.5. What is 3 times 2.5? 7.5 minus 1. 6.5. Yes! You find the pattern? Did you find the pattern? That every time you add 1.5 to the exponent, the next one is 8. The next one? Yeah, 9.5. Next one? Yes! Awesome! And yeah, we already know that f of 4 is e to the 11. So yeah. Okay, now put this in your calculator. Yeah, bring your calculator all the time. So put this in your calculator. What do you get? Give me 3 decimal places.
38,530.748.
Thank you. 48. Thank you. So this is our answer. Okay, everybody? So your homework, I think it's homework 2. You're going to have exercise. You're going to draw the rectangle, and then you're going to pick either to use the left end point to compute or use the right end point to compute as your height. Okay? All right. Any questions about this problem? All good? Okay. All right. So the area A of the region S that lies under the graph of the continuous non-negative function f is the limit of the sum of the area of the approximating rectangles. So A area is the limit of the right Riemann sum as n goes to infinity. Can you see when n goes to infinity, your area of the rectangle is very close to the actual area? I think I have some GeoGebra animation. Let me see. Did I put this in our course? Probably not. But in my calculus ones. Okay, the calculus one, I put it here. Yes. Okay. I mean, this is one example. Yes, like this. And you see as the n changes, we have the upper sum is closer to the lower sum and is closer to the actual integral. Yeah. So you can see the number of rectangles changing. Ooh, the area is closer and closer to each other. Yes. Okay, good. All right, we mark. In fact, we can pick any point. So the right Riemann sum, we pick the right endpoint. We can also use the left endpoint, then we have the left Riemann sum. Or we can use the midpoint, then we have the midpoint Riemann sum. So that point, it could be any point on this interval. Because the number n goes to infinity, then the width goes to 0. So it really doesn't matter you pick the left hand point, the right hand point, or any point. Their heights will be close about the same. If your n goes to infinity, the width goes to 0. Okay. And so that is the how to approximate the area using the Riemann sum. And how do we do the examples? Okay, look at the table. The table shows the rates of population growth for the Barry town for several years. Use this table to estimate the total population growth from 1970 to 2000. Okay, so we have the years and we have the rates of population growth, and we have those in the table. Okay, so that is the rate of population growth. To get the total population growth, we actually want to integrate. Okay, so the total we want to integrate. So integrate of t dt from 1970 to 2000. Okay, we want to compute that. And the problem tells us compute the left endpoint sum and the right endpoint sum. Then pick the average to approximate it. So we need to do both left endpoint and the right endpoint. Okay, let's do that. So let's draw two different pictures. Okay, the first picture, let's see. So we have this one and this one. Okay, let's say here 1970, 1980, 1990, and 2000. So we have 1.5, 1.9, 2.2, and 2.4. So we have the first dot here, the second dot here, and then this one and this one. So the table just give us 4 dots on the XY plane. Yes, everybody? We want to do the left endpoint Riemann sum and the right endpoint Riemann sum. Let's do the left endpoint Riemann sum. Do you mind that I copy this picture? Because then I don't need to draw it again. Okay, so this is a good thing about using Word. Okay, let's do the left endpoint Riemann sum. And do you like purple? Let's use purple. Okay, so we know we want to cut it into 3 rectangles. And we use the left. So look at this rectangle. We use the left endpoint. We draw this one here. That's the left endpoint. And this rectangle use the left endpoint. And here we use the left. Do you see those 3 rectangles? What's the width? 10. Yes, the width is 10. So the left endpoint sum, how many rectangles are there? 3. So we put L3. This stands for left endpoint sum, and we have 3 rectangles. Okay, the first rectangle. What's the width? 10. What's the height? Yes, 1.5. See, height is 1.5. Second rectangle. What's the width? 10. What is the height? 1.9. Yes. The last one, what's the width? 10. What's the height? 2.2. Ah, do you see 10 times 1.5 is 15 plus 19 plus 22? What is your answer? 15 plus 19 plus 22. Use your calculator. 56. Oh, good stuff. Yeah, very good. That is 56. Right, everybody? So that is the left endpoint sum. Oh, let me make it closer here. Okay. And now let's compute the right endpoint sum. So we also want to cut this into 3 rectangles. But look at the first rectangle. We use the right endpoint as the height. So use this endpoint as the height. So we draw it like this. And then the second rectangle, use the right endpoint. The third rectangle, use the right endpoint. Is that okay, everybody? Yeah. The first rectangle, what is the width? 10. Do you see the width? They're the same? Just the height's different. So the right endpoint sum, we also have 3 rectangles. Okay, look at the first rectangle. What's the width? Then what's the height? 1.9. Yes. Second rectangle. The width. The height. Yes. Last rectangle. The width. And the height. Yes. Okay, so we have 19 plus 22 plus 24. What is the answer? What? 65. Oh, okay. So 65. Which makes sense because the right endpoint sum is more area than the left endpoint sum. So 65 is bigger than 56. Makes sense. And the problem side, we need to take the average. Okay, so the average Yeah, 56 plus 65 and then divided by 2. What do you get? 121 divided by 2? 60.5? Yes. So that's the answer. Okay. See, in this case, we don't even know what's the formula of the function. Do we need to know the formula of the function? No, we don't need to. We just know a bunch of points, and then you can use the left hand point to compute the left hand point sum, or use the right hand point to compute the right hand point sum. And then you can take the average. Hopefully, the average can approximate the results better. Okay. Okay, that is example 2. Any questions about example 2? Not good? Okay, now more definitions. So we just talked about indefinite integral. Okay, so indefinite integral. Indefinite integral is, we have the integral sign as and the f of x dx. This is the antiderivative plus c. So this is a family of antiderivatives. So antiderivatives. Okay. Now today, definite integral on an interval closed interval a to b is a number. It represents the area under the function from a to b. So it's also the limit. The Riemann sum tells us that we can take n goes to infinity, but actually you can the general Riemann sum is you don't restrict all the rectangle have the same width. You can allow them to have different width, but you need all of the width goes to 0. Okay, this is a general Riemann sum. Okay, provided the limit exists. And if it exists, we say the function f is integrable on AB. And the AB are called the limits of integration. F of x is called the integrand. X is the variable of integration. Right? So some terminology. Theorem. If a function is continuous on AB, or if f has only a finite number of jump discontinuity, then f is integrable on AB. Do you still remember what is jump discontinuity? So you have a function like that, right? So you can still compute the area under the integral if you have a finite number of jump discontinuity. You just integrate each interval and then. Okay, so net area. Consider the region R bounded by the graph of a continuous function f and the x-axis between A and B. The net area of R is the sum of the area of the parts of R that lies above the x-axis minus the sum of the area of the part of R that lies below the x-axis. So, because of this definition, do you see the width is always positive? But your function, if your function is above the x-axis, then your function is positive. And then this sum will be a positive sum, right? But if your function lies below the x-axis, your f is negative. Your width is positive, but your f is negative. You get the sum is a negative sum. So therefore, the definite integral represents the x, the net area. Well, that is when the function is above the x-axis, your area is positive. And when your function is below the x-axis, the area is negative. Okay, everybody? Mm-hmm. All right. So how about the total area? Okay, the total area. I also want to write it down here. So total area equals integral from a to b. Now put absolute value around the function f. So what does e2 is whenever the function is negative, you kind of flip it over to make it positive. So this is the absolute value of f of x. It's always greater or equal to 0. Therefore, you get the total area, which is the area above the x-axis plus the area below the x-axis. So we get the total area. If you learn some physics, did you need to take physics class? No? Okay, yes, okay. So the net area is like the displacement. And displacement is the integral of the velocity. Yeah? And the total area is like the distance. Okay, so displacement is the integral a to b of the velocity dt. The distance is integral from a to b of the speed. Speed is the absolute value of the velocity. Okay, like here, I'm standing. Let's say this is the positive direction. Okay, I go here 2 meters, and I go this way 4 meters. My displacement will be negative. But my distance is the total distance I traveled. It will be 2 plus 4 is 6. Okay? So your net area, sum of the positive area and negative area can cancel. It's the total area. You don't want them to cancel. You want to add them all up in the total area. Okay. Next. Properties of definite integral. Okay, the definite integral from a to a, what does that mean? So you have a function. Let's say a is right here. From a to a, do you see? This is the segment, right? This is a line segment. What is the area of a line segment? 0, because the width is 0. So therefore, the integral from a to a is 0. Therefore, it does not really matter about the endpoints. The integral of the closed interval is the same as the integral on an open interval, AB. Just a single point does not matter. And then next, the integral from B to A is the same as negative the integral from A to B. Why is that? Okay, if you remember the definition from a to b f of x dx, that's the limit. And you have the Riemann sum is f of the xk times change of x. The change of x is b minus a over n. Okay, if you can remember. Do you see here b minus a? If you swap them. Okay, so this is the same as negative a minus b over n. Do you agree? It's negative a minus b. So this is the negative integral from b to a f of x dx. So if you interchange the limits of integration, you gain a minus sign in front of it. Okay, next one. From if you have integral of sum, that's sum of the integral. Kind of makes sense, right? Do you still remember the one of the sheets I gave you at the beginning? We have integral of sum, the sum of integral of subtraction of difference is difference of integral. That is also true for definite integral. And constant multiple. You can put the constant in front of the integral, right? Do we have parallel rule or quotient rule? No. Be careful. And the fifth one, we have, let's say, A, B, C is here. Integral from A to B is the same as integral from A to C plus integral from C to B. Does this make sense, everybody? Okay. Oh, and here we also talk about the total area. It's the integral of absolute value of x dx. Okay, now exercise. Use the graph to calculate the following. Okay, how about you guys take turns to answer my questions? Wait, what is the integral from 0 to 2 f of x dx? 0 to 2, what's the area? 2, right? Yeah, so 0 to 2, the area is 2. Okay, next. Will, what's the integral from 2 to 4?
2.
Integral is the area from 2 to 4. What's the area here?
5.
5. But it's below the x-axis. So you say
Negative
5. Yeah. So above is positive, below is negative. So that's negative 5. Okay, Sarah, how about the integral from 4 to 5? 2, yes. So we got 2 here. And next page, how about the integral from 0 to 5? Huh? Yes, very good. We add them up together. Some of the positive cancel with the negative, right? It's okay. So 2 minus 5 plus 2 is negative 1. That is the next area. Okay, so this is the next area. If I ask you what is the total area, which is from 0 to 5, absolute value of f of x dx. What is that? Mackenzie? What is the total area? If you add them all up, what's the total area? Total. So you don't have negative anymore. All of them you count them as positive. Yes, very good. That it would be 9. Okay, everybody. So this example, you can distinguish between next area and the total area. Okay, good. So continue. Alright, so B of x will represent the area bounded by the graph and the horizontal axis and the vertical line t equals to 0 and t equals to x. Okay, so for the following, we want to evaluate B of x for x equals to 1. So what's B of 1? So B of 1 represents your x is 1 right here. So you're talking about the area. Right? So B of 1 is this part. Okay. So we have a square and a triangle. What's the area of this square? What's your width? What's your height? 1 times 1. So this square is 1. How about this triangle? What's the area of the triangle? 1/2. Yes? 1/2 times 1 times 1 is 1/2. Oh, so we got this B of 1 is 1 plus, you can say 0.5 is 1.5. Is that okay, everybody? Okay, next. B2. Play. B2. So now our x is 2. So right here, it will be okay. Imagine one block is 1, right? So 1, 2, and half of a block is 2.5. Yes. Oh, sorry, you said 2.5. Okay, good. All right, good. B3. Okay, B3. 3 is right here. Well, what's B3? So B3, right here. What's the area? How many blocks? If this is half of a block, right? This is half a block. So the
Oh, so that's half of the block.
yes
Oh, okay. So
area.
4.
4, yes. Right, everybody?
Yeah.
Good. 4. Okay. Next, B4 is so right here, Sarah. Yes, 5.5. Can everybody see that? 5.5. Okay, B5, page 6. Yes. So actually you can compare. B4 is 5.5, and then B5 is you have a half block, one more half block. So you have 1.5. You can also think of that way. All right. So yeah, this problem we have the graph, and then we can calculate the area. You know the area of a square and triangle, then we can figure it out. Okay, example 5. So the velocity of 2 cars are shown in the graph. From time the brake was applied, how many seconds did it take each car to stop? And from the time the brake was applied, which car traveled further until it came to a complete stop? Okay, part A. Okay, so part A. What's the time the brake were applied? How many seconds did each car? Okay, so the red car. How many seconds? Is 40 seconds. Oh, let me see. Do we start to count here, or the brake was applied? The brake is applied at 20. 20 seconds. The brake was applied at t equals 20 seconds. And how many seconds? So the red car, it takes 20 seconds. And the blue one takes what? 40 seconds. Right, everybody? Okay, so part B, from the time the brake were applied. So this is the brake applied here, right? Do we look at the previous ones? We don't look at this. Only look at after the brake. And which car travel further until it comes to the complete stop? So we want to calculate the area. Right, everybody? Because this is the velocity, this is the velocity, and we know displacement is the integral of the velocity. Okay, so the red one. Do you see here? We have what is the width? This is 20, right? What's the height? 80. So 20 times 80 is, yeah. So the area, okay, area is 1/2 base times height. So 20 times 80. And do you see we cancel? So we get 800. Right, everybody?
Yes.
And the blue one. We have what? This one. So we have 40 and wait, is it 40?
Yeah.
Oh, okay. So area 1/2 40 times 40 is, what is that? 800? Oh! So they actually travel the same distance after the breakup. Okay, yeah, let's continue next week. Have a good weekend. Thank you.